In this video, we're going to look at the other type of variation, which is inverse variation. Now, this isn't a linear function, but we talk about it here because we want to make sure that we show the relationship between both direct and inverse variations. So an inverse variation is a relationship where the two variables have a constant product. So in direct variation, the quotient was constant. Now, this is going to be a constant product. So when one variable increases, the other is going to have to decrease in value so that product remains the same. We have two equations that we use for inverse variation, and both of these are perfectly good answers for any time that you're being asked for the equation. So if this were a test and one person gave the y equals k over x equation and the other person gave the xy equals k equation, both of those are accepted as the answer. You don't have to worry about which one you're going to write. Depending on the problem or what you're being asked to do, one form of the equation may be more helpful than the other. And k still represents our constant of variation. So this is what the inverse variation looks like. We're always going to have this y and this x here, and we're going to fill in our constant of variation. In the table now, if I look at my product for that constant of variation, we're going to have a constant product all the way down. If I look at my graph is a little goofy looking. One thing that you'll notice is that we don't have a point that goes through the origin like we did with direct variation. In fact, we don't have any points with an x-coordinate of 0 at all, because if I make x 0, that would mean that 60 would be divided by 0, which would be undefined. In the same way, you'll notice that we don't quite have any y-coordinates of 0, because if I start with 60 and I divide it by something, I'm never going to get an answer of 0. This creates two kind of boundary lines on the graph, and these are called asymptotes. So these aren't part of the graph, which is why we draw them as dotted lines, but you want to think about them as invisible fences. Like if you have a dog in your yard and you have an invisible fence, they can get really, really close to the invisible fence, but they're never quite going to touch it. Our graph is going to get closer and closer and closer and closer to the y-axis, but it's never going to touch it. And same thing, it's going to get closer and closer and closer to the x-axis, and it's never going to touch it there. Our graph has two pieces, one that lives in quadrant 1 and one that lives in quadrant 3. So we want to make sure whenever we graph that we graph negative x values and positive x values so that we get both parts of the graph. We don't want to leave out any piece. So same thing as before with direct variation, we can use our formula to see if a table represents an inverse variation. So I'll add in my column, and this time we'll have the product. And now we just go ahead and multiply and see what we get. So here we have 40, 40, all the way down. So we know that this one is an inverse variation. If we take a look at our next table, here we get 135, then we have 540, and as soon as I have two that are different, I can say that this is not going to represent an inverse variation. When we graph an inverse variation, we're going to use the same process. We create a table and fill in the points. If you want to use your calculator, the equation has to be in the form y equals, so we would just rearrange our terms here. So we have y equals 8 over x. I can type that in on the y equals screen and then go to the table, and I can get some points that I can use to plot for my graph. So you can see how much space we have here. If we have negative 8, that means that y is going to be negative 1. If we do negative 4, we'll get negative 2, negative 2 and 4. You'll notice that I can't plug in 0 here because that's not going to work. It's going to be undefined. So we're going to leave 0 out, and then we can fill in our positive values as well. And I'm going to extend our table here a little bit. And then we would also have 8 and 1. So we want to make sure that we have enough points so that we can get a complete picture of the graph. You should have at least 3 points for both curves in here. You don't want to have any less than that because then you're not going to be able to see the true shape of the graph. So we plot each of our points, negative 8, negative 1, then we have negative 4, negative 2, negative 2, that should be a negative 4 there, and then negative 1, negative 8. When you graph these, you want to do your best to kind of show the curve as you connect the dots. It's a little hard on the computer here. I'm not going to grade you on how nice your graph looks, but it should cross through those points that you plotted. Then we do the same thing on the other side. And you'll notice that our graph kind of matches up. This graph has symmetry, so the two parts are going to look very similar, just reflected, and we'll talk about reflections and transformations a little bit later on. And so if we connect this corner, we can see the two parts of the graph, and again we can see those two invisible asymptotes that we're going to get really close to, but we're never quite going to touch them. When you're graphing, you don't need to include the asymptotes. Just know that they're there. And lastly, we have our applications, and these look very similar, actually exactly the same as direct variation, but now we say that they vary inversely. So those are the keywords that you're still looking for. Go ahead, pause the video, and see if you can answer each of these questions. Alright, so if we look at our first question, we're given that y varies inversely with x, and that y equals 40 when x equals 8. So we go into our xy equals k, substitute those in, and we get the k equals 320. So we have these two options here for our equation. Then we look at the problem. We're given a y value, and we're asked to solve for x. So the equation that's going to be most useful to me right now is probably that first one, xy equals 320, because then there's only one step that I need to take to solve. So we substitute our values in, and we get x equals 32. For the second question, we have the time it takes to fly, our y, that varies inversely with the speed of the plane, our x. We know that the trip takes 6 hours at 900 kilometers per hour, so that 6 is going to be a y, and the 900 is going to be an x. We can substitute that in, and we get a k value of 5,400, which means we have these two equations here. And we want to know how long that same trip would take at 800 kilometers per hour. 800 kilometers per hour is an x, which means we're looking for y. So I'm going to use my second equation here because that's already solved for y. So we substitute the values in, and we get 6.75 hours.